in order to help you with Lewis structures and resonance structures, I'm going to do some of the examples that are in the Moodle worksheet. And the first is this thiocyanate ion, which has really interesting and useful resonance structures that we're going to go over. So for any Lewis structure of a molecule, you've got to be able to know the connectivity of the atoms there. This one's pretty straightforward. We've got a sulfur bound to a carbon, bound to a nitrogen, and all this has a negative charge. So as I said in the video, we're going to total up the number of valence electrons present in each of these. Sulfur gives us 6 valence electrons, plus our carbon gives us 4, plus our nitrogen gives us 5. If we total that up, we get 15 valence electrons, and that's odd. And when you see an odd number for that, you need to pause and think, well, what the heck? You know, bonds and lone pairs are made of pairs of electrons, so having an odd total number of valence electrons is strange. That would mean we'd have an unpaired radical electron, and that's unusual. Doesn't mean it doesn't happen, but it's unusual. So we don't just have 15 total valence electrons here. We have to remember that this is an ion, and so it's negatively charged. It has one extra electron from that negative 1 charge, and so we have a total of 16 valence electrons to work with. Those 16 valence electrons have to connect these atoms together, and we're going to try to make them all happy with the octet rule. And so from our 16 valence electrons, we've already used 4 of these for the 2 bonds that are connecting the 3 atoms together. So we're left with 12 valence electrons to work with. Now in my video I said the next thing I do in this procedure is to find out how many electrons each atom would need if they just had lone pairs. Right? So this sulfur has 2 electrons. To get its octet, it would need 6 more electrons. So I'll say need over here, and I'm going to need 6 to make the sulfur happy. This carbon has 4 electrons, so it needs 4 more. If we were to add it as lone pairs with no one sharing. This nitrogen has 2, it's going to need 6 more. And so we would need 16 electrons if there was no sharing with bonds. Now at this point I look and I would need 16 if to give everybody their own electrons. I don't have 16, I only have 12, so that these atoms are going to have to share, right? And for every 2 electrons that I'm lacking, I'm going to need an extra bond. So I'm going to add, 2 more bonds here. Since I'm lacking 4 electrons, I'm going to add 2 more bonds. Now this is where resonance structures come into play. I have a choice of where to add these 2 bonds, and that choice will lend itself to form other resonance structures. Okay, so let's just add these 2 bonds in the most obvious place. I'll add one here and one there. Okay, but let's show the other choices. Right, I could have added both right here, and my final choice would be to add those 2 electrons, or those 4 electrons, those 2 bonds between the carbon and the nitrogen. Those are all my choices, and these are going to be the framework for all of my resonance structures. Now none of these are done. We have to finish our Lewis structure for each of them, but it's pretty straightforward. When I added these 2 bonds, remember I had 12 electrons to work with. I added 2 bonds, so I have to subtract the 4 electrons that are required for those 2 bonds. So now I have 8. And if you've done your work correctly, these 8 electrons I should be able to just put onto our structures as lone pairs to make everyone have a complete octet. So let's start up here. We have 8 electrons. This sulfur needs 4 in order to complete its octet. Carbon is happy right now. This nitrogen needs 4. So that's my final 8. I used up my final 8 electrons. Everyone has their octet. Everything's fine. Now, these 8 electrons will also be used to satisfy these other resonance structures. In this case, this nitrogen is going to need 6. Only have 2 left. Carbon's happy. Sulfur has 6. It only needs 2. Everything should add up nicely as we fill in these 8 electrons as lone pairs on our remaining structures. Okay. So we have 3 resonance structures here. All of them satisfy our Lewis structure rules. Each atom has a complete octet. We didn't use too many electrons. We didn't use too few electrons. And so these are all legitimate resonance structures, right? So we have to judge which one of these is the best, or if they're all equal to each other. And so the way to do that first is to assign formal charges to each of the atoms. Now, if you remember, formal charges can be done with an equation. This sulfur has 6 valence electrons. So let me do this up here. Here's 6. I subtract the number of bonds, and I subtract the number of lone pair electrons. So we have 4 lone pair electrons. And so in this case, this sulfur has a formal charge of 0. This carbon, if you did the work, would have a formal charge of 0 also. 4 valence electrons minus 4 bonds. And this nitrogen over here, without even calculating it, must be a -1 formal charge. The formal charges of all your atoms will add up to the overall charge on the molecule. So this nitrogen has to be the -1. And it is. It's 5 minus 2 minus 4 is -1. If I'm quickly going to assign formal charges to the rest of these, this sulfur here would be +1, this carbon would be 0, this nitrogen therefore would have to be -2. This sulfur is what? 5. This one has negative. No. This would be -1. -1, 0, and therefore this nitrogen has got to be 0. Okay. Now in judging between different resonance structures to see which one's more stable, you want the least amount of formal charge. Okay, and so this one looks like it's going to be in 3rd place, right? That doesn't mean it doesn't exist. It just means it's less stable than the other 2 because it has this abundance of formal charge, which is very different than these other 2. Now, how can I judge between these other 2? They have a similar quantity of formal charge. And really the question is, would I rather have a -1 formal charge on the sulfur or a -1 formal charge on the nitrogen? Well, the next sort of level of discrimination for these resonance structures is to try to put negative charges on the more electronegative atoms. And if we look at the periodic table, sulfur's got a little bit lower electronegativity, and so, or a little higher electronegativity, and so I would rather have this -1 charge on the sulfur than on the nitrogen. And so this is how I'm going to rank these formal charges. Okay? Now, what it means is really that these electrons are resonating back and forth between the carbon and the sulfur and the carbon and the nitrogen. They're spending time in both places resonating. They're spending probably a little more time between the carbon and the nitrogen than they are between the carbon and the sulfur. And that's what this ranking tells us. These 3 are legitimate resonance structures because they're fair and legal outcomes of our Lewis structure protocol that we've learned. All the octet rules are obeyed, and we haven't used too many or too few electrons. If you don't obey the octet rule or use too few or too many, then those aren't resonance structures. Okay? Resonance structures come into play when we're adding bonds and we have a choice of where to add them.